All right. About that time. Go to your Instant Learning. Make sure you have the new packet. That's a copy of Unit 5 that I would have taught from in a normal school year, especially when I really want to do a lot of AP reinforcement. So it's Unit 5. Make sure you both find it. I have some of you that are in the dual, some of you are not dual. Let me know real quickly if you don't find it. I'm going to assume you're finding it or already had found it. It looks like 7 of you came in already and you're in the chat. So you already chatted. It looks that way. I'm going to share my screen. I'm going to try to teach. Nobody gave me any feedback on the presentation I did from the Wacom tablet versus the iPad. So I'm going to do the Wacom right now only because it's right here. I've got prepared my iPad just in case. Okay, trying to share, but I can't find that screen that has it. Oh, there it is. Looks like that, and I've already started off where we're jumping to, okay? This was applications derivatives, so we're gonna jump down to, I don't know if that matches up because it might not be 46, 47, it's in that vicinity, sometimes renumbering, it didn't happen, but we're gonna talk about particle motion, and we're gonna just go and review that. So I've got to scroll down to many pages here. Let's see. Not there. Not there. Okay, those are the theorems. If you did the live session from the presenters yesterday, that's what they were doing. All those are all those theorems. And so that's what I'm skipping right now is very good stuff, very good practice problems that go over the, and if you end up doing anything extra above it, there's even a quiz here, I think that's a quiz, even a quiz there, but there it is, particle motion problems. All right, I'm gonna do some notes in the lecture area, and then we're gonna jump to some free response problems, okay? Gotta move you guys out of the way because, let's see. Okay, that helps. All right. Particle motion. Let's see. Let's talk about the difference between average and instantaneous velocity. Okay. If we're doing the average, it's pretty much all about the slope of a secant line, if you recall. So let me see what I'm going to write here. We'll start with, suppose, we'll call it P for particle. P of T is a function, we'll call it is a position function. In other words, where is it at? Where is it at in space? Usually we're doing just 2 dimensions, X and Y, but a lot of times it could be just the X. We talk about on the number line from -3 to 7, and then all you care about is, let me change color just for effects. If the particle started here and then it moved over here, then it moved back here, and then it moved more that way. Keeps going back and forth, and we're just talking about the X position. But it doesn't really move back to my black. Okay, so P of T is a position function. And of a moving, let me take off this, of a moving object. Could be a dot, could be a car, could be a spaceship at time t. We're going to talk about the average velocity. Your average velocity will be, we call that the average rate of change. average rate of change of position. We would make that, let's say we're going from A to B. So if I'm going from A to B, I would say F of B minus F of A all over B minus A. So we're moving from point A to point B. So doesn't that look like the slope formula to you? It does to me. Can anybody yell out before I write it out? What is instantaneous velocity? Nobody. Okay, I'll just pretend I'm by myself. P prime of t. It's the derivative at a certain point. Okay, it's a derivative at a certain point. Do I need to write anything here? All right, I'm not going to do this practice problem that has P of t, and then it does the average, and then I think we do instantaneous. So I'm not going to find the slope between, if I was doing it, I would find for the average, I would find it between 1 and 3. You know, P of 3 minus P of 1 over 3 minus 1 would be your average velocity. Okay, that would be that. And so I could easily plug in 3 and 1 into this equation. I would probably use my calculator only because sine of 3, I don't know what it is. And definitely sine of 1, that one I could probably do. Sine of, no, I can't. It's 1 radian probably. So no, I probably wouldn't do that either. Calculator. This would be the derivative. It would not be, it's in your wheelhouse. Oh, wrong letter. Oh, my iPad's so much easier to go back. Okay, it'll work. P prime of t would be the derivative, and be careful because it's got a product rule here. You're going to have to do a product rule. And then you're going to have to I really want P prime at 1.5. What is the instantaneous speed at 1.5, whatever that meant, seconds, units, whatever. Up in the problem, he called it centimeters per second. So you would use centimeters per second. This is very important part, the units. Usually, if you don't put the unit, you don't get credit for the answer. So it's 1 point loss. All right, let me move down from there. I hope you found that page okay. Do I want to talk about average instantaneous? Oh yeah, let's talk about average acceleration. Okay, it's not going to be any different. We have P of t was my position function. Okay, position function, and V prime of t, which was equal to P prime, well, as it was P prime. So your velocity function, that's not velocity, your velocity function is P prime of t. And you should realize that your acceleration function would be P double prime. P double prime of t, or we can take the first derivative of velocity. So how will I put my definitions? I'll do the same thing. If P of t is a position function, and P prime of t is the V of t, the velocity function, then, I'll put then, scroll down a little bit, yeah, then A of t will be equal to the change of we're doing average. I want to do average. Let me erase the A of t. So I want to put the average. Well, I can add it in front. Yeah, the average acceleration will be v prime, assuming again that we're traveling from A to B, will be v of B, v prime of B, minus v prime of A, still over B minus A. It's the secant of the velocity function. Wait, did I mean to put the v? Somebody, so you're not helping me out. No one's telling me. It's not v prime, just v. And so instantaneous acceleration would be, as we set up at the top, would be your derivative of velocity. Okay? So there's a good problem here using the exact same function, E of t times sine of t. And then there's your 1 to 3. So I'm not going to do that work. Let me jump to the next slide there. And then there's I like all of this stuff here too. You know, what happens when, if your velocity was 0, what does it mean about position? Those are very good things for you to think about, good thinking problems. Same thing with acceleration. Of course, I'm not teaching this from scratch. I'm just trying to get to this page uses a hypothetical graph, and just, I'm not going to answer any of those questions for you. You just need to realize that obviously if this was he's calling the position function S, okay? So I can imagine this being where S prime of t is equal to 0. I can imagine that this, at this point, S prime of A is probably greater than 0 because it's increasing. It's rising to the right. Whereas, so is this one. At E, it's also rising to the right. At C, it's decreasing there because the derivative, the tangent at that point, is falling to the right. Then I have another, looks like a extrema. So here probably is your derivative is 0. So those are talking about velocities, acceleration. Let's talk about acceleration. Looking at this graph here, let me change color for the acceleration because it's all about the concavity when you're looking at the position function. So if I look right in here, this is definitely concave down. So that would be your acceleration. Your A of t would have to be less than 0. That's deceleration. Whereas over here, I see concave up, which would mean your acceleration, why did it get darker? I'm writing heavier. Is the A of t would be greater than 0. So you can look at that picture and have an idea, maybe not know exactly where your points of inflection are because you don't know the function. So that won't help. So I got those things were asked in there. All right, let's go to the next slide. 5 commandments of particle motion. I think this is good to fill in because when you're taking your AP exam and you're dealing with particle motion, there's some truths, the 5 commandments. The first of the commandments will be, let's see what I write, let's see, V of t, I don't like that color. It's too dark. There it goes. Oh, took me to the next slide. Drop down again. Go back to my black. Black is faithful. I'm going to say V of t equals to 0. Your velocity is 0 at t equals, I'll use some letters. I'll just say b to d to t equals to d. What am I looking at? Oh, I'm looking at the wrong page. I don't want that one. I want positive. Sorry. Okay. Here it goes again. I'm sorry. You can, hopefully you're using pencil, right? If velocity is positive, you know what that means. That means it's greater than 0. Then the object, you probably can even finish it before I say it. The object is, if we're doing like particle motion going left and right, you know, bouncing from the right, going to the left, then if the object is moving right, okay, that's important. If velocity is negative, anybody there?
Yes, sir. It's moving left.
Thank you. Object is moving left. It also applies up and down as well. If you're on a 2-dimension and you're going up, well, you would if it's positive, it's increasing on the way up. It's not going straight up necessarily. Okay, this one, only my physics students might be able to think of commandment number 3 about the speed. The speed of an object. It's not the same as velocity. Speed in analytical terms is actually, I'm going to give you a little secret. If you do velocity of a function and they ask for speed, we know speed, I want it right here, is the absolute value of velocity. Keep that in mind. That's a little secret. The speed is increasing when the signs of velocity and acceleration, and can fill in the blank, are what?
Positive.
If they're both positive, you're correct. What if they're both negative? If they're the same. They both can be both positive, and you're absolutely right. Now, if they're not the same, when we say the speed then is decreasing, it's slowing down if the signs, I should say plural up there, I don't know, signs of velocity and acceleration are different. So yeah, if they're both positive, 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 or both negative, negative, the object is speeding up. If you have one of each, it doesn't really matter which one, I messed up on that, or that, then that's what we're talking about. Okay. And sometimes it's usually like part D, they say, tell me something about the speed. Where is the particle decreasing or increasing at this time? And you got to go back up and look at your other work where you did the velocity and acceleration at that same value that they're concerned about. All right. What if the velocity is 0? But the acceleration, E-R-A-T, is not equal to 0. Well, that means the object is momentarily. That means momentarily stopped. Because velocity is 0, it did stop, but because the acceleration is not 0, what probably happened, because an object in motion tends to stay in motion, there's still some acceleration force wanting it to move. So chances are it stopped, blink of an eye, it stopped so that to change directions. It's still moving, even though we say it stopped, but it stops momentarily means blink of an eye. And now there's a function where we're going to ask all those things, and I think it's healthy for you to do them. I'm not assigning it to you because next Tuesday is your AP test. You know, I'm going to work on this free response. I think that would be a bigger bang for the buck right now. You want to do extra work and you want to, practice. That's great. Let's talk about this graph here. This came from 1998. It's modified. Oh, the author modified it a little bit. The graph of the velocity in feet per second of a car traveling on a straight road from 0 to 50. So right away, I know that's my A. It's where it starts. That's where it's ending. And it's shown below in the table of values that line up to that graph for V of t at 5-second intervals is shown to the right. So basically, the data is the same. Okay, this is a good problem because you're looking at a graph and you're looking at data that you could have gotten from the graph, but I think the author was nice enough to put dots. I didn't do that. The author of this curriculum, he put those dots to line up and show you what's happening. All right, what is A asking? Determine what intervals of time is acceleration of the car positive. Well, what do I know about intervals of time when acceleration is positive? And we have to give a reason. That doesn't mean tell me what it is. Just define it. I'm gonna start it out for you. A of t is positive, means greater than 0. Then what must be true? You can only talk about position and you can talk about velocity. So which of those would be a better indicator of acceleration being positive? Velocity or position?
Velocity.
Right, that would be a better thing. Velocity must be positive. Or I should say increasing. That'd be better to say increasing. The velocity is increasing. Because think about it. The change of velocity, V of B minus V of A over B minus A, you would, if this is my acceleration, you would want it to be a positive number. So you want it to be increasing. You want it to be slope of the velocity looks like that. The slope of the velocity is in the increasing direction. And he says, give a reason for your answer. We are going to look at that table and let's see. What do I have? Velocity? I have velocity right here. This graph was velocity. I didn't even have position function anyway. So it was a trick question when I said, would I use a position or velocity? I didn't even have position. So all I have is velocity graph. So you can look here and see, just answer this question. Do you think from here to here, that change of velocity is positive? Just somebody, yes or no? Here to here.
Yes.
How about here to here? And here to here?
Yes.
Here to here? Here to here?
Yes.
Here? How about right here? Up here? At the top? What do you say there?
I mean, if it's getting to the top, then yes, but not at the top, right?
Good. Getting to the top, yes, it's constantly. So why don't I define that? So you think there's a problem right here? You think there's a problem there? What happens there?
It changes direction.
Changes direction, so it's just period where it's going to be momentarily stopping.
Absolutely. That's a relative max of the velocity. So I'm going to say it is increasing on the interval. I'm going to go open interval 0 to 35 for sure. Was there any other possibly increasing intervals? You see anywhere else it's also increasing?
$45 to $50.
Yes, exactly, right here, 45 to 50. So this is my justification. Well, actually, I wrote the justification first, and I'm going to go union. I think she said 45 to 50. And you can use interval notation. You could also use, the expanded 0 less than t less than 35. And 0 is, time is greater than 45, but less than 50. You can do that. Next part. Now we're going to actually find something. Find the average acceleration over the interval from 0 to 50. 0 to 50. Oh, okay. Let me change color here. 0 to 50. Here to here are values of velocity. And he wants the average. Is that what he said? Average. Yes. Average means what? Slope of a what? Somebody make me proud. Slope of a what? Slope of a secant line, guys. It's a slope of a secant line. So I just need these order pairs, 0, 0, and 50. Looks like 50, 70. Does that look okay to you? Or no, am I wrong? I think it is. Maybe it's at 70. I mean, look at the table. What could it possibly be? I think it's at 50. At 72. So the actual number is 72. 0, I was right on 0. Okay, so I'm going to write average. I'll leave it in purple. Average acceleration will be the slope of that will be v of 50 minus v of 0. And you can switch them. It doesn't really matter because when you switch those two and then I end up switching the 0 and the 50, it all comes out to the same answer. And so v of 50, we say is 72. V of 0 was 0. And that would be all over 50. And that gives me, anybody who good at that math? 72 or 50? 36. I can leave it. You know what? On the AP test, don't waste a lot of time. What if it's not calculator? Just write it out. You don't even have to reduce it. You can leave that answer. But I'm a glutton, so I'm going to go 36 over 25. Oh, I need my units. It was seconds and feet. So I have to write feet per second squared. C. Find the approximation for the acceleration of the car at t is 40. All right, he just said an approximation for the acceleration of 40. Go back up to my picture. 40. I want to change color so we can see it. 40, 40, 40. Up. Right here is the dot. And that would be this line right here. He wants the approximate, what did he say? Acceleration. Well, he's got a dot right there. So he's really talking about the slope of the tangent line. You see what I'm saying? But I can't do this slope. I don't know the function. So let me erase what I wrote over it so I can, well, where's my eraser? Right here. Let me get rid of what I wrote on it so I can see it better. How can I approximate, back to my pen, the tangent right here? It almost looks like for part of it, it's writing on the curve. What would I do to estimate? He said it'll be perfect. Could I just go from this point to this point and talk about that secant? That to me looks like a very good approximation. It's almost lined up with what would the derivative line be, if not parallel to it. So I'm going to use those. That means I'm at 35 and I'm using 45. 35. Oh, look at this. It's on this side and this side is how we used to approximate it. So let me write out what I have based on, show the computations. So here it goes. I'm going to write A of t, which was equal to v prime of t. Well, actually, I don't want t. I want the number. What number was we using? 40? Yes, no?
Yes.
Let me do to write it. A of 40, which is equal to v of 40, is approximately, I'm going to write v of, I think I was using 45, minus v of what was before 35, I think, over 45 minus 35. So those numbers, what were those numbers? I can move back up, but you can tell me. What was 45 on the table?
60.
60. What was 35?
81.
81 over, I can do this, 10. I can do that. That looks to me like a negative 21 over 10. So that'd be well, I'm still doing an approximation of what that was supposed to be. Approximate negative 2.1. And it's still going to be feet per second squared. Are you surprised that it's negative? Look at it. Are you surprised it's negative? No, look at it. It is rising to the left. It is decreasing the acceleration. Is the speed of the car increasing or decreasing at t is 40? Well, what do I need to tell that? I would need v of 40. I would need that. I'm going to write that out. I need v of 40 and a of 40. It's the only way you could tell analytically, okay? So did I do a of 40 somewhere? I did an approximation right here. I did, this was approximately negative 2.1. That's my scratch note. Did I do v of 40 anywhere? They never asked me to do v of 40. So what I'm going to do, I got to figure it out, don't I? Do I have it in the table? Or is it on the graph? Somebody save me. Save me from myself. 40. What's v of 40?
Maybe you just, oh, it's 75?
Yeah, it's just 75. That's why he didn't have me do it. It's in the table. 75. Now, this is just scratch work. That's not what the authors want to see. So you can do scratch work any you want. You got to write something. I'll probably write what I found in there. I'm going to say v of 40 is 75. What were the units again? Not that it matters. I'm just being, it was feet per second, right? So I'm going to say feet per second. But really all I really care was I could have just said greater than 0. And I could have wrote a of 40 is less than 0. Therefore, since v of t and a of t have different signs, Okay, I can't, I'm out of room here. We're gonna move this. So let me move. I got a zoom bar in front of me. Since they're different signs, the car must be what? Increasing or decreasing? Signs are different.
Decreasing.
What'd you say? Decreasing or increasing?
Decreasing.
Very good. Decreasing. At, just make sure you tell it where, at t equals 240. Because it's not always decreasing. It just will happen to be there, okay? Put my bar back down. You don't know what I'm doing here. I got a bar there. All right, that was a good problem. Very good problem. And, you know, I think it's modified because he wrote the dots on it. I remember this problem. It's pretty accurate to what they asked that year. Let's see, next page is something I want. Okay, let's do another one. Let's do 2000. It's a little newer, and it's two runners, A and B, run on a straight round racetrack from 0 seconds to 10 seconds. So that's just 0 to 10. There's my A and B. The graph below, which consists of 2 line segments, shows the velocity. It's a velocity graph again, and we are in meters per second. Hopefully I won't forget, meters per second. Oh no, that's a runner 4. 2 runners, A and B, are running on a track. The graph below consistent. It shows the velocity of runner A. Okay, it's just runner A. That picture was not for B. Velocity in meters per second, a runner B. Is a function. All right. So we're looking at 2 different forms of velocity from a graph and from an equation. Okay, so I think I got that. I might want to rewrite that equation down farther. I'll have one of you repeat it to me because I'm going to scroll down so your paper, hopefully you can tell me what it is. We're going to need it though. We're going to need that equation. So let's talk about A. He wants find the velocity of runner A. So runner A comes from the what? The graph or the equation?
The graph.
The graph. So what I need is, I want the velocity from the graph at 2 seconds. Okay, here's 2. I'm very lucky that this is just a line because he told me it was a line. So since that's a line, I don't even have to estimate. This slope right here must be what's on the graph. Must be, if I just figure out where it is there. Velocity at time t is 2. Find the velocity of runner. What am I missing here? Guess I need to know what this.
Wait, isn't there a formula? Oh yeah, can you just plug in T?
For this, for V, yeah, for runner B though. I want runner A, and the graph below consists of 2, shows the velocity of runner A. So what is the velocity? Maybe it's going to be hard to figure it out what it is. What do you think it is?
Sorry. Wait, wouldn't it just be the Y value? Or
Do you know exactly what it is?
7?
Exactly. Yeah, that's a good guess. But I think you won't. How do you know it's not 7.1 or 7.001? I think it'd be better, since it's just a line, we take these 2 endpoints. Let's take a second. And since he's not asking us to show any work, he's asking just what is it and indicate your units. We probably should find the equation of this line because it is the Y value like you said. But Y is equal to mx plus b. So you're right, y equals, I need the slope. So let's find the slope real quick. 10 minus 0 over 3 minus 0. Look how close you were. 10/3 times x plus the y-intercept. Well, that would be the 0. So the equation is, yeah, you're 10/3 times x. So what happens? What is the y value at time t is 2? Would that be 10/3 times 2?
Yes.
Oh, that's 20/3 then. And so he didn't say show your I'm not going to rewrite the work down here because he didn't say to calculate it, but we had to. Runner A, we know for a fact, is going to be 20/3 feet. And I'm an AP grader, so I know for a fact that they would have seen that anyway and realized you did that work. It doesn't have to necessarily be right here if that was required. I don't think it was. Runner B though, Claudia, is when I need that equation. Runner B needs that equation for V of 2. So can you give me that equation since you were looking at it? And I'm going to plug in a 2 in place of T. Is that equation right there? Can you read that back to me, Claudia? I thought she left me.
No, it's just that, so it's 24t.
Times.
Wait, let me just read it really quick.
Yeah. Go ahead. It was 24t, wasn't it? Over. Okay, I'll go look. 2t plus 3.
Yes, 2t plus.
So that's 24 times 2 over 2. What was it? I already forgot the bottom. It was 2t plus 3, right? So 2 times 2 plus 3, that will be 48 over 4, 5, 6, over 4/7. Annette, she's back again. That would be meters. Oh, I'm reminding myself. I didn't put my, oh yeah, I did. Is it meters or feet? It's meters. I just double checked it. It was meters, wasn't it? Yeah, hello. Meters per second, meters per second. That's all you had to do. Find the acceleration of runner A and the accelerator B at time t. So I'm at the same time period. So I'm talking about, again, runner A and runner B. And we're talking about accelerations. Now, if I go up and look at A, tell me about what we're talking about for runner A at t times t. What am I talking about? This is the velocity curve. And I put a little m here. That line had slope. We used it over here. But wouldn't that m be actually the acceleration?
Yes, because.
Yeah, it would. Mm-hmm. So what is the acceleration? That would have been the slope of that line. Remember, it was 10/3. And let me write that out. Acceleration is 10/3. Would it be x or t at some t?
No.
No, it's just 10/3, right? Yeah, it's just 10/3. That was it. Now you want to get fancy, you could have said that the velocity was equal to 10/3 t plus 0. V prime is 10/3. That means the acceleration was 10/3 meters per second squared. But I want to know at, so that's why that t wasn't part of the acceleration. It is That is acceleration for runner A because it's constant. So A of 2 as runner A will just be 10/3 because it's the slope of that line never changes. That slope never changed on that segment. Now runner B is different. Runner B is going to take some work. You're going to have to say A of t equals the velocity of t derivative. And so let me go look back up. Is it an easy derivative of that function? No, it's going to take quotient rule. And it's not hard, but I didn't want to do it. I still don't want to do it, but they're making us. The bottom, what is the bottom? Read it back to me. No one's going to do it. 2t plus 3.
Yes, it was 2t plus 3.
And the derivative top? Is just 24, right? So derivative top is 24 minus the top, which was 24t, times derivative bottom, which looks to me like just a 2, all over the bottom, which was, I'm looking up there in my green there, 2t plus 3 squared. So I'm going to put 2t plus 3 squared, which is, let me separate my work from, help me out. Oh wait, what did I do? That is the formula to simplify it. What's it simplify to? 24 times 2t, that's 48t plus 24 times 3, 72 minus 48t. Huh. Now it seems like it's going to go to 0, I think. Look at it, guys. Tell me. 2t plus 3 times 24 minus 24t times 2. You're not talking. Did anybody do the derivative?
I got the same thing.
Okay. What's the denominator? Oh, leave it as squared for now. Oh. Leave it as 2. It was 2t plus 3 squared. Does 48t minus 48t cancel though? Or are we, does it cancel? I think it does. So that looks pretty simple, 72 over that. But I need to know what the acceleration at 2 was. So there's nothing in the top, 72. The bottom, 4 plus 3 is 7. 7 squared is 49. I'm not going to reduce it because I don't have to. So I'm just going to write meters per second squared. All right. C. At t is 2, is the speed increasing or decreasing of each runner? So we're going to do speed of A, runner A. Maybe I don't have to write a whole lot. You can look at all the work we've done. Speed of runner B, but we do have to justify why or why not. So runner A, let's see. What are we looking for? Velocity, runner A. It's positive. See that? Velocity is positive. Acceleration of runner A. Positive. See that? So I can say runner A is what? Somebody tell me what runner A is doing. What's runner A doing?
It's increasing.
Yes, runner. So in running terms, runner A is speeding up, speeding up, or increasing. Since v prime of 2 and a prime of 2 had same signs. Whoop. Where's my button that allows me to extend my room? There it is. Same signs. Runner B, let's look up there. Runner B. Runner B, let's see. Velocity was 49/7 positive. So I'm gonna make a little note here. It's positive. Runner B's acceleration is, was it also positive? Common sense, Mr. Cartwright. You're running a race. Who's going to be slowing down? Hello? Runner B. Speed. I can't spell. So I do, I'm in a hurry trying to get as much done as I can with you. Is increasing as well. That's not very exciting since her speed or her velocity at 2 and her acceleration at 2 are the same sign. Look at all the justification you have to do. It's almost like an English paper. All right, those were very good AP problems. Typically, when you take your paper pencil test, they plan approximately 15 to 20 minutes for a response. But this year might be slightly, I think you're doing 6 problems. And so that's not gonna be any different than normal. I think you're still gonna have to do, it's not like last year. Last year they had 3 free response and no multiple choice. They also cut out some units last year. All right, 2002, say we've gone through, this is not the full problem. It's only A and B, so let's see, can we get through A and B? That takes me out of those. Yeah, I'm gonna want you to do these. Guys, I was very liberal on getting stuff done and not putting a time and a date, let you keep working, but I was not happy with the quiz submission. I wanted something put up, and there was some did and some didn't put anything. So I'm gonna want to see this posted by 9 a.m. Today's Tuesday, Thursday. I guess I gotta, yeah.
This is due 9 a.m. Thursday.
Pardon me?
So wait, can I read the top again just to make sure?
9 a.m. Thursday. It's the practice right after this lecture here.
Okay.
So let's finish this last one. Object moves only on the x-axis with the initial position. So it's 0, 2. And he's given me the velocity is at time t. Any time greater than 0 is given by this function. So that's my velocity after 0. Okay, after 0. What's the acceleration? Well, I hope if we know that v of t is sine of pi thirds t, then a of t is my acceleration, should be the derivative. The derivative of sine is cosine. Keep everything in the argument, which is pi thirds times t, but I got to multiply by the chain rule. And you know how those people in the evening, they sing a song every time. Every time it's chain rule. And I'm not going to do that. I'm not going to humiliate you by singing. Pi thirds, that would be the chain rule. And that's just a of t, but I need it at 4. So a of 4 will be the cosine. Let me put the pi over 3 first. It's just a constant. Pi over 3 times the cosine of pi over 3 times 4. That's 4 pi over 3. And that equals, and this may not be a calculator problem. So you have to ask yourself, what kind of, well, pi over 3 is 60 degrees, 60 times 4. We're talking about a 240-degree angle. That's in this quadrant down here. And this is a 60-degree reference angle. So across the street from a 60 is the square root of 3. Hypotenuse is 2. That must be the 1. That's negative, and that's negative. So that could be important. So pi over 3, and the cosine of this angle is adjacent over hypotenuse. That's negative half. Multiply negative pi over 6. Do I have units? No, you didn't give me any units up there, so I don't have to put any units. B, consider the following two statements. We're going from 3 to 4.5. We know for a fact the velocity is going to be decreasing. That means V of t is going to be less than 0 between 3 to 4.5. And then between, what am I doing here? We also know that the speed is decreasing from the same interval. Interesting. What does that tell you? Right now, without me doing any work, what does it tell you if the speed is decreasing? What does that imply? V of t and A of t had what?
Different signs.
Different signs. So that tells me if V of t was decreasing, that means it was negative. So A of t must be greater than 0 in that interval. And those are just my scratch notes. I'm thinking out loud. I might use that in my write-up. Okay, I might. What's he asking? Are either or both these statements correct? Oh, okay, hold on. So that's what I did summarize this. I think we're still looking at this situation over here with this velocity and the acceleration that we created. Are either or both of these? Let's see. Let's look up and see. How do we know about? Well, that's a lot of work, isn't it? How am I going to look at that? We only look at 4. We looked at acceleration at 4, and he's talking about the interval between 3 and 4.5. So is 4 in there? 4 is in there. I can use t is 4 since I have some information in there. And we know it's consistent. Whatever it is there, the values from 3 to 4.5 are the same. So I can use that. All right, so let's look at statement 1. Let's look at statement 1. What is V of 4? Somebody yell it out at me. V of 4. And I also need to know what A of 4 is. I want to see what my speed is based on that information. I want to know what the speed is to see if is my velocity decreasing? So he's asking, is this true? Is velocity decreasing? Did I do velocity at 4? Here's velocity right there. What is velocity at 4? That's 4 pi over 3. Use that same triangle. Was in this quadrant. And that was a 60-degree angle. Same measurement. Square root of 3. 2, and a 1. Is that the triangle I had up here? Oh, I'm in the wrong quadrant. See, people aren't helping me out. 240 degrees was down here. So that was across from that angle was a square root of 3. That was a 2. That's a 1. So what's the sign of that triangle? It's in quadrant 3. Sign's negative. So I know for a fact, this is less than 0. And A, we did that up there. A, we did it, and it was negative. It was also less than 0. So the speed was increasing, wasn't it? Because they're both negative. So I know that to be true. So is statement 1 correct? Is the object decreasing?
Yes.
The object is increasing if both signs are the same. Okay, that means velocity is decreasing. So at t is 4. That means on the interval, that means from t from less than 3, but or greater than 3 and less than 4.5, the object is also decreasing. Or no, I thought you said it was increasing. Well, this is just velocity, right? So it was decreasing. So that's true. So statement 1 is true. And I'm almost done here. I know somebody logged off already. That's the last one. Statement 3. Is the speed decreasing? I did acceleration. Are they both the same sign? We said the speed is what? Did we have different signs? I thought we had different signs. We had the same signs. So the particle is increasing. So for statement 2, since v of 4 was less than 0, and a of 4 was what? Somebody tell me what it was. I don't want to scroll up. You're helping me out. That's why it would take longer. A of 4 was less than 0. That meant increasing speed. He said speed is decreasing. So that's false. Statement 2 is false. All right. That was all I wanted to get through. As I said, that where am I at here? Next page starts those problems. I want you to work on them. It's about 3, 4, 5, 6, 7, 8, 9, 10, 11. That's probably about it. Yeah, that's it. And there's another kind of particle motion we can look at afterwards. One more lesson. Running out of lessons. Running out of time. If you're done, I'm done.
You only have one more class to do, right, sir?
Yeah, you only have one more class, and I'm probably going to be posting up an AP test for Friday, even though I don't have you Friday, right? Today's Tuesday. Wednesday.
We had Thursdays last time, sorry.
Thursday's your last pass, but it's going to be there for Friday and Saturday, and I'm going to review it on Sunday, and we can have some discussion, either whoever wants to go